This video presents a technical summary of a study published in Physical Review E, Volume 109, focusing on the behavior and modeling of polarizable polymer chains. The key question addressed by the authors is, how do induced dipoles, formed along a polarizable polymer chain in an externally applied far-field electric field, interact? And how do these interactions influence the chain's conformation and mechanical properties? This matters because traditional models have typically only accounted for the interaction between the applied field and the induced dipoles on the polymer segments, neglecting the long-range dipole-dipole interactions between segments themselves. These dipole-dipole interactions decay slowly with distance, proportional to the inverse cube of the separation, leading to significant non-local effects that cannot be disregarded without incurring large errors. The approach of this work involves using a self-consistent statistical field theory that fully incorporates these long-range dipole-dipole interactions in modeling the polymer chain's behavior. By doing so, the authors aim to provide a more accurate description of both the polymer configuration and its mechanical response under external electric fields, thereby improving upon prior models that omitted these interactions and hence underestimated their impact. Figure 1 illustrates the fundamental physical scenario considered in this work. A polymer chain composed of polarizable segments is placed in a far-field external electric field, denoted by E0. This external field induces dipoles in each segment of the chain. Crucially, these induced dipoles interact with one another through dipole-dipole interactions that decay slowly with the cube of the distance between segments. Such interactions introduce long-range, non-local effects that significantly influence the overall behavior of the polymer. The authors emphasize that prior modeling efforts generally accounted only for the interaction between the applied external field and the induced dipoles, but neglected the interactions among the dipoles themselves. Such omission leads to large inaccuracies. By fully considering these dipole-dipole interactions, the authors aim to better capture how the polymer's microscopic dipolar interactions dictate its larger-scale configuration and mechanical response under the applied electric field. To quantitatively describe the polymer chain, the authors adopt a statistical mechanical model called the worm-like chain model. This model treats the polymer as a continuous, three-dimensional space curve parameterized by a contour coordinate. The chain consists of n coarse-grained segments, each with length a, so that the total contour length is LC equal to the product AN. The persistence length, lambda, characterizes the chain's stiffness and is the contour length scale over which segment orientations remain correlated. Here, the authors focus on a flexible polymer with a persistence length much smaller than the total chain length. Specifically, lambda over LC equals 0.01. Figure 2 visualizes these kinematic quantities, the spatial trajectory of the polymer chain, RS, where the contour coordinate S runs from 0 to 1, representing the normalized chain length. This mathematical framework allows construction of partition functions that capture the statistical distribution of chain configurations by considering both the effect of the external field potential acting on induced dipoles and the intrinsic chain entropy. These detailed variables set the stage for integrating the long-range dipolar interactions in their statistical field theory approach. Figure 3 presents the baseline simulation results when dipole-dipole interactions are neglected, showing how the system behaves if only the applied electric field interacts with induced dipoles. Here, the authors fix the polymer chain ends at positions plus minus 0.075 along the unit vector E2, maintaining a fixed end-to-end vector length of 1.5 times the square root of AN. The externally applied electric field E0 is set as a uniform constant vector of unit magnitude along the E2 direction. Panel A shows the electric field distribution, which appears constant in space and equal to the applied field, as expected without dipolar feedback. Panel B shows the chain segment density, which is highest near the constrained ends, indicating segments cluster around the fixed chain ends, mainly along the end-to-end vector. Panel C shows the polarization distribution, which is close to 0 on the scale of the plot. the induced dipoles align with the applied field direction but have negligible spatial variation without interdipole coupling in this baseline case. These results form a reference for later comparison to the full model with dipole-dipole interactions included. Figure 4 provides a direct comparison of the polarization distribution P, contrasting cases when dipole-dipole interactions are neglected versus fully accounted for at two key orientations between the applied electric field and the polymer chain. Panel A shows the scenario where the applied field theta E naught equals 0, meaning the field is aligned with the chain, and panel B corresponds to theta E naught equal to pi over 2, an orthogonal orientation. In both panels, the left image displays polarization without dipole-dipole interactions, while the right image shows results including these interactions. A striking difference arises. When dipole-dipole interactions are included, the magnitude of the polarization is at least an order of magnitude larger compared to when they are ignored. The arrows depict vector directions, and background colors represent polarization magnitude. Its enhancement occurs regardless of the field chain relative orientation, underscoring that these interactions substantially amplify the induced dipoles, altering both their spatial distribution and overall intensity. The authors interpret these findings as demonstrating that neglecting dipole-dipole interactions significantly underestimates the polarization and thus the electromechanical response of the polymer chain. Building on the previous comparison, Figure 5 explores how varying the orientation theta E0 of a fixed magnitude applied electric field affects the polymer chain's electric potential, field, and polarization when dipole-dipole interactions are fully included. Two contrasting cases are shown. When theta E0 equals 0, meaning the applied electric field is orthogonal to the chain end-to-end vector, panels A, B, and C display the electric potential, electric field, and polarization respectively. In this case, the induced dipole distribution appears approximately uniform along the length of the chain. Conversely, when theta E0 equals pi over 2, meaning the field is aligned parallel to the chain, panels D, E, and F show the same quantities but exhibit that the dipoles concentrate primarily near the chain ends. Correspondingly, the electric field distribution follows from the electric potential. It is roughly uniform along the chain length in the orthogonal case, but highly concentrated near the ends in the aligned case. Importantly, the local magnitudes of the electric potential, electric field, and polarization are overall higher in the orthogonal orientation case than in the aligned orientation. These observations indicate that the relative orientation between the applied field and polymer chain markedly influences the spatial distribution and intensity of induced dipoles and fields, underlining the coupling between geometry and the long-range dipole interactions. In Figure 6, the authors analyze the elastic response of the polymer chain under stretch for the case when the applied electric field is orthogonal to the chain end-to-end vector, theta E0 equals 0. The figure plots the force required to stretch the chain as a function of end-to-end length, providing insight into the mechanical behavior of the polymer coupled with the electromechanical fields. Insets show the corresponding distributions of the electric field and polarization at three different stretched lengths, scaled as an to the power of 2, an to the power of 3, and 3an to the power of 4. The arrows indicate vector directions, and the background color reflects magnitude. As the chain is stretched, the electric field and polarization remain approximately uniformly distributed along the polymer, but increasingly concentrate along the end-to-end vector. This suggests that mechanical stretching influences the spatial redistribution of induced dipoles and local electric fields within the chain structure, while the elastic force curve captures how these coupled interactions translate into mechanical resistance to deformation. Figure 7 presents the elastic response of the polymer chain when the applied electric field is aligned parallel to the chain end-to-end vector. Theta E0 equals pi over 2. As in the previous figure, the force required to stretch the chain is plotted against the chain extension length. Insets show the associated electric field and polarization distributions for three stretched lengths, an 1/2, 2an 1/2, and 3an 1/2. Unlike the orthogonal case, here the electric field and polarization are predominantly concentrated near the chain ends. This localized distribution evolves as the chain is stretched, reflecting how the mechanical deformation modulates the electrostatic environment within the polymer. The authors note that the elastic force response itself is largely unaffected by changing the field orientation, highlighting that while the mechanical behavior is fairly robust, the internal distributions of electric field and polarization are sensitive to the relative orientation between polymer chain and applied field. This figure complements Figure 6 to show that polymer electromechanical coupling depends strongly on geometric orientation of the applied field. In conclusion, this study demonstrates the critical importance of including long-range dipole-dipole interactions when modeling polarizable polymer chains subjected to external electric fields. The authors show that neglecting these interactions, as done in prior work, results in large errors, notably underestimating the polarization magnitude by at least an order of magnitude. By employing a self-consistent statistical field theory based on the worm-like chain model, the work captures how these dipolar interactions non-locally affect both the spatial distribution of induced dipoles and the mechanical response of the polymer. The findings highlight that the relative orientation between the applied electric field and the polymer chain's end-to-end vector plays a significant role in the distribution of induced polarization and local electric fields, with orthogonal orientations yielding more uniform distributions and higher intensities, while aligned fields concentrate effects near chain ends. While the elastic force stretch response remains largely insensitive to field orientation, the internal electrostatic fields and polarization distributions vary substantially. This comprehensive approach improves the fundamental understanding of electroresponsive polymeric soft matter and has potential implications for designing materials with tailored electromechanical properties. Future modeling and experimental studies can build on these insights to better harness electric fields to control polymer configurations and mechanical behavior.